All right. So we've got for ourselves a roller coaster, and I want to make sure that this is really clear. This is really kind of a special roller coaster, and by special I mean not realistic. Okay? Like a lot of things, we're gonna make some assumptions. This is a major assumption. This is a roller coaster that has no friction and no drag. Really, a roller coaster would have both friction and drag. Friction in the axles of the wheels, drag as the cart crashes into the atmosphere. There'd even be thermal energy loss as the track itself heats up as you roll over it, right? So we're assuming no energy dissipation, and that actually is like a major assumption. But as this cart goes, it's going to start off at position A, go to B, loop around to C, up to D, and then all the way down to E. And so I've got some heights here. It looks like this is height A, this is height B, this is height C, height D, and finally height E. You get to the end of the track. And if it's a true roller coaster, not a powered ride, this would have to be the case. Notice the height of height A. What do you notice about all the other heights compared to height A? Yep.
They're all lower.
They're all lower, yeah. And they would have to be because the energy you have at height A would have to give you enough energy to get over all those other heights, right? If this hill was higher than height A, I might not make it, depending on the speed that I had at position A, right? So the total mechanical energy would have to be enough to get us over. All right, so as I look at this again, I notice that there's 3 sig figs here.
We didn't need the key. We just had to press a button.
Oh, go figure. All right. Well, that's good. It's nice when things just work when you press a button. Speaking of making things just work, if we want this thing to, if we want to work through this thing, we've got total mechanical energy equaling gravitational potential energy plus kinetic energy. And you know, one of the reasons why people tackle roller coasters is to say that the total mechanical energy depends on your mass, your speed, and your height. It does not depend on what direction your speed is pointing in. It's just a scalar addition. And so it doesn't matter if I'm going to the right at the bottom of a roller coaster hill or to the left at the top of the loop. It's just the speed I care about, not direction, okay? And that's kind of a nice thing to keep in mind. No reference frames. So if I figure out the total mechanical energy for this system, I'm talking about mass times acceleration due to gravity times a height where I know the height value. In this case, I know the height at position A, plus 1/2 m times, if I happen to know the speed at the same location, which I do, I know the speed at position A. I don't know the speed at any of these other locations, at least not yet, right? So I have enough information to figure out the total mechanical energy at position A. And so that's why I'm picking on position A, because I know the mass, I know the height at A, and I know the speed at A. So I can pull all the pieces of the puzzle together. And when I plug in my values, I've got this roller coaster that has a mass of 500 kilograms. It's on Earth, 9.81 meters per second squared. It's at a height of 20 meters. And it's moving along at a speed of, what does it say? 0.500 meters per second. Don't forget to square it. And notice that's a really slow speed, but I think that we all kind of know when you get to that top of that first hill on the old-fashioned roller coasters, you go like, oh! You ever been on one of those guys? And you're like, you're coming up to the top of the hill. If you ever go to Canada's Wonderland or any of those Six Flag type parks, they pull you up that first hill and there's like a chain and you hear like click, 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 click. And you get the butterflies, not from the motion, but from the anticipation. And you get to the top of that hill and then everybody screams as you go over the hill, right? But right at the top of that hill, you're going real slow. Not stopped, but real slow, right? So I do all these calculations to calculate my E total at that first position, that first peak. It's a big number. And it starts with a 9. Did anybody get it yet? Yep. Ooh, nice. Oh, nice. I love it. I love it. And then if I was going to round it off to 3 sig figs, 98,162.5 joules ends up being, well, if you like, 9.82 times 10 to the power of 4 joules. So therefore, the total mechanical energy of this roller coaster Oh, was there?
Yeah,
981,062?
yeah.
Oh, is that right? Did anybody else get that?
What?
Oh, no, you're right. Decimal.
No decimal? Is it right? 98,162.5? Okay, I want to make sure we don't have typos. That's good. Okay. 9.82 times 10 to the power of 4 joules. Honestly, I thought that it was 98,000. Is it 98,000?
Yeah,
Yeah.
put gravity as negative.
Oh, okay. All right. Now, this might not be such a mathy thing, but it says, what's the total mechanical energy at B, C, D, and E? What do you guys think?
Same.
Should be same, yeah. If conservation of energy is a thing and we're not losing energy due to drag or friction or anything, if this is a totally conserved roller coaster, E total at A, B, C, D, and E are all going to be 9.82 times 10 to the power of 4 joules. And we could make a little statement, due to conservation. Of energy. Okay. And then part C, find the gravitational potential energy at position C. Well, I'm going to have to pan up the page here. Now, we've already written all these givens out. I don't think we need to write it out again. But at position C, I'm at 13 meters above the ground. So we're going to come down here. If I want to calculate gravitational potential energy, EGC is equal to mass times acceleration due to gravity times height C. 500 kilograms. 9.81 meters per second squared. Height C, we just said, was 13.0 meters above the ground. That's at the top of the loop-de-loop. You want to go back and look yourself. So this seems like a fairly straightforward calculation. This one should start with a 6, though. Make sure you get it. Who's got it? Yep.
I got 63,765.
Nice. 63,765. And there's no decimals, right? It's just like, just so? Yeah? Okay. So 3 sig figs later, going to tell us 6.38 times 10 to the power of 4 joules. And of course, we could have a therefore statement. Therefore, the gravitational potential energy is. That seems fairly straightforward. And then it says find the kinetic energy at point C. Well, okay, this seems an awful lot like something we've maybe seen before. But we could say, well, E total at C is going to be equal to EGC plus EKC. We know that means that EKC is going to be equal to E total C minus EGC. Just getting EKC all by itself. Taking the EGC over to the other side, leaving that isolated EKC all by itself. And we're saying, okay, well, E total C, we figured that out earlier on, unrounded is 98,162.5 joules, minus EGC, which we just figured out, unrounded is 63,765 joules. I'm just going to write the answer on this one. 34,397.5 joules. Can you guys confirm? Did I get that one right? I don't want to have my own typos, yeah? Okay. All right, so then we can do a little thought flow arrow here, and we say, okay, well, then that means that EKC is approximately 3 sig figs, 3.44 times 10 to the power of 4 joules. And we could write a therefore statement, but I think we kind of get the idea of how we'd express this stuff, right? So for our full communication, write a little context for this. And then how fast is the car going? Notice again, it says how fast, not what's its velocity. I definitely could tell that if it's at the top of this loop, as it gets to the top of the loop, can you guys see that its velocity's direction would be to the left? Because I understand how loops work. But it doesn't ask for the velocity, it asks for the speed, how fast, right? So we're just looking for the magnitude here. So it says, how fast is it going? Well, I know that if I've calculated EKC in part D, then EKC is 1/2 MVC squared. And I'm just isolating for VC. I'm going to give myself a little breathing room here and go up here where I have some more space. I would say 2 times EKC, and I'll show all my steps this time, is M times VC squared. I just multiply both sides by 2. Then I could divide both sides by M. Cancel, cancel. Now I'm at a spot where I can say VC squared is equal to 2 times EKC over M. And of course I'm going to square root both sides, which means that I can calculate VC is equal to 2 times, well, EKC was equal to unrounded 34,397.5 joules divided by the mass, 500 kilograms, all square rooted. I really haven't left myself a whole lot of space here. Not even for a therefore statement this time. But VC equals, I think the answer starts with a 1. Anybody get it? You think you got it?
11.729.
Nice. 11.7299 meters per second, or we could say approximately 11.7 meters per second. Now that's still pretty fast going around this loop. But roller coasters are a thrill, so we'd have to do some research to figure out if that's realistic or not, right? But 11.7 meters per second based on the values that we've got. Now here's the challenge. I kind of walked you through that. For your own sake, make sure you can do this. I've got the answers right here. If you follow the same pattern, you should be able to get the answers and check yourself. The speed at position D should be 9.92 meters per second, and at position E should be 19.8 meters per second. I feel like 19.8 meters per second is way fast, but like, give it a try. See if you can do it. Remember, this isn't a realistic roller coaster because there's not even any drag, so this is just a theoretical value anyway, but see if you can follow the patterns and get to the answer, okay? And again, I'll just like leave all the values there just in case you need them.